Introduction to Module 2. Welcome to Module 2 of Engineering Graphics 2. In this module, we focus on specific technical elements of mechanical and workshop drawings. You'll learn how to create and interpret cam profiles, gear systems, subassembly and full assembly drawings, correct workshop drafts, and read blueprints with confidence. Let's begin with cam profiles. Lecture 1: Drawing Methods for cam profiles. Cam profiles are essential components in mechanisms that translate rotary motion into linear motion. They are commonly used in engines, automated machinery, and timing systems. A cam profile drawing defines the shape and motion path of a follower as the cam rotates. To draw a cam profile accurately, the following must be understood. Type of follower: this could be flat-faced, roller, or knife edge, each with its own design implications. Cam motion: different types include uniform motion, simple harmonic motion, or cycloidal motion. Base circle: the smallest circle from the cam center to the follower path. Trace point path: this is the curve the follower tip traces, forming the cam's profile. Drawing a cam profile involves plotting displacement diagrams and transferring that motion into polar or Cartesian coordinates to map the cam contour. Attention to scale and motion type ensures the cam performs as designed. Understanding cam design is essential in automation, robotics, and precision timing mechanisms. Lecture 2: Presentation and Drawing of Various Types of Gears. Gears are mechanical elements that transmit torque between rotating shafts. Their design and presentation in engineering drawings must be clear to ensure correct manufacturing and function. There are several types of gears, each with unique features and uses. Spur gears: the most common type, with straight teeth aligned parallel to the shaft. Helical gears: teeth are cut at an angle to the face of the gear, providing smoother operation. Bevel gears: used for shaft at an angle, commonly 90 degrees. Worm gears: used for high reduction ratios with a screw-like appearance. Rack and pinion: converts rotary motion to linear motion. Gear drawings typically show the following: pitch circle, addendum and dedendum, pressure angle, number of teeth, gear ratio, direction of rotation. Proper labeling and sectional views are critical when detailing gear assemblies. Engineers must be able to visualize how gear teeth interact and ensure clearances are appropriate. Lecture 3: Assembly and subassembly drawings. Now, let's look at assembly drawings, a crucial aspect of mechanical engineering documentation. An assembly drawing shows how individual parts come together to form a functioning product. It identifies all components in the system, how parts are oriented and connected, fastening methods such as screws, bolts, or welds. The order of assembly. A subassembly is a smaller group of components that form part of a larger assembly. For example, in an automobile engine, the crankshaft assembly may be considered a subassembly. Key features of a good assembly drawing include a bill of materials, listing every part and its quantity. Exploded views, showing how components fit together. Sectional views to reveal hidden components. Reference balloons connecting parts to the parts list. Properly presented assemblies help machinists, technicians, and engineers understand how to build, inspect, and repair machinery. Lecture 4: Workshop Drawing Correction and Modification of Symbols. Workshop drawings must reflect current manufacturing practices. Errors, outdated components, or improvements in design often require corrections or modifications. Engineers or draftsmen must update dimensions, tolerances, material specifications, manufacturing instructions, standard symbols and annotations. Drawings are revised using standard revision blocks and clearly indicated changes. Each modification is dated and signed for accountability. Understanding drawing symbols is key. These symbols include representations for welds, surface finishes, machine operations, tolerances, fastener types, Correcting and modifying workshop drawings is a routine yet critical part of engineering communication. It ensures that the final product meets design intent, safety standards, and production efficiency. Lecture 5: Reading and Interpreting Blueprints. The ability to read blueprints is fundamental in engineering, manufacturing, and construction. A blueprint is a detailed technical drawing that communicates all necessary information to construct or fabricate a part, structure, or system. Blueprint reading involves understanding orthographic projections, top, front, and side views, dimensions and scale, line types, solid, dashed, center, and cut in plain lines, symbols for materials, words, finishes, and tolerances, sectional views that reveal internal features. Blueprints also include title blocks, which provide drawing title, date, scale, drafter, checker, and revision history. Notes and legends to explain specific instructions or exceptions. Reference callouts that link to other drawings or documents. A competent blueprint reader should quickly identify key information such as part dimensions, tolerances, materials, finishes, and assembly steps. Practicing with real-world drawings enhances this skill, allowing students to bridge the gap between theoretical knowledge and practical application. Lecture 6: Integrated Applications in Design and Manufacturing. Bringing all these elements together, let's consider how engineering graphics support the design and manufacturing process. From concept to product, drawings serve as the blueprint of production. Initial sketches communicate concepts. Detailed component drawings provide manufacturing specifications. Assembly drawings guide the construction or assembly process. Blueprints provide comprehensive documentation used on the workshop floor. In industries such as automotive, aerospace, consumer products, and civil infrastructure, these documents reduce errors, standardize practices, and improve efficiency. The use of CAD, computer-aided design, has revolutionized this field, enabling rapid updates, simulations, and electronic sharing of detailed drawings. However, the foundation still lies in the drawing principles covered in this course. Lecture 7: Industry Standards and Quality Assurance. Before concluding, it's important to mention standards and quality assurance. International standards such as those from ISO and ANSI govern engineering drawing practices. They define acceptable formats, dimensioning rules, tolerancing systems, and documentation procedures. Adhering to these standards ensures compatibility across departments, companies, and even countries. It enhances collaboration and product reliability. Quality assurance includes checking drawings for accuracy of dimensions and annotations, consistency in symbols and conventions, completeness of views and details, legibility and clarity. Errors in engineering drawings can lead to costly manufacturing mistakes. Therefore, every professional must strive for clarity, precision, and conformity to standards. Module 2 Summary. In this module, we explored key components of advanced engineering graphics. CAM profile design and representation, drawing and understanding gear systems, assembly and subassembly documentation, correcting and modifying workshop drawings, interpreting blueprints and technical documents, integrating design communication into the manufacturing process, following international standards and ensuring quality. Mastering these skills equips you to communicate complex technical information clearly and efficiently, whether you're designing a new machine, interpreting architectural plans, or fabricating parts on the workshop floor.